We are in the middle of the proof of the Fredholm alternative. So we have shown that if T is a compact perturbation of identity, then the null space of I minus T is finite dimensional and the range of I minus T is closed. Now we come to the important property, which is really a finite dimensional property, namely I minus T is 1 1 if and only if it is onto. Okay, so this is part C. So assume n of I minus T is singleton 0, that is I minus T is injective. So to show, so assume, if possible, that V1 equals the range of I minus T is strictly contained in V. Okay, so this is not equal to V. So we have to get a contradiction. So V1 is closed implies it is a Banach space in its own right. So if X belongs to V1, X belongs to V, then you have T of X minus Tx is equal to I minus T of Tx. Okay, so this I minus, so T of something in V1 is again in V1, because this again in the image of I minus T. So this implies that T of V1 is contained in V1. Okay, therefore T maps V1 into V1 and it's a Banach space, it is compact. Okay, and therefore it also has closed range. Okay, because I minus T, therefore I minus T has closed range. Okay, so let V2 be equal to I minus of V1. Okay, so then V2 will also be strictly contained in V1. Why? If not, for every X in V, okay, so for I minus Tx belongs to V1, and if you assume that V1 is equal to V2, implies there exists a Y in V such that I minus T of such that I minus T of X equals I minus T of square of Y, because it is I minus T of X is in V1, it should be the image of something, it should be in V2, V2 is nothing but I minus T square of Y, and then I minus T is injective, implies that X equals I minus Ty, implies X belongs to V1, that is V equals V1, a contradiction. Okay, because we are assuming V is strictly bigger than V1. Therefore, thus V strictly contains V1 and that strictly contains V2. So inductively we proceed like this. We get a sequence of closed subspaces Vn, and you have V contained in V1, strictly contained in V2, strictly contained in V3, and so on. This should not end, because at any stage if it ends, then all of them will back up, and then you will get V1 equal to V, and that will be okay. Okay, so we have, and Vn is what? I minus T power n of V, and Vn plus 1 proper subspace closed subspace of Vn. Okay. So by Riesz lemma, so I hope you remember Riesz lemma, there exists a un in Vn such that norm un equal to 1 and the distance of un from Vn plus 1 is strictly bigger than or equal to any positive 1 minus epsilon. I am taking epsilon equal to half. So you have this is greater or equal to half. Okay, so now T of um minus un can be written as un minus tun minus minus tum. So we have to, this un minus has to be removed, so plus minus un. Okay. So assume n is bigger than m. Then un minus tun belongs to Vn plus 1. Minus tum belongs to Vm plus 1. And then un itself belongs to Vn. And then you have, what do you have? N is bigger than m, therefore Vn plus 1 is strictly contained in Vn, which is strictly contained in Vm plus 1, and that is strictly contained in Vm. Okay, so therefore you can write T of minus un is equal to which is in Vm minus some w, where w is in Vn or Vm plus 1, Vn plus 1. It's in one of these three things, and therefore w belongs to Vm plus 1. If you look at where all it belongs and these inclusions, and therefore so from these two it follows that w is in Vm plus 1. Therefore norm of tum minus tun is greater or equal to 1/2. So what does this imply? So you have a fixed distance between any two of them, therefore un is bounded, its norms are all 1, and tun does not have a Cauchy subsequence, which is a contradiction to the fact that T is compact. And therefore this implies that V1 equal to V, that is range of I minus T, is all of V. So if it is 1 to 1, then it is in fact onto. So now we have to claim the other one. So conversely, let range of I minus T equal to V. So it is onto, we have to show that it is 1 to 1. So then n of I minus T star equals range of I minus T perp, and that is V perp, that is singleton 0. Okay. So now T compact, we know this implies that T star is compact and it is 1 to 1, and therefore by earlier argument we have range of T I minus T star equals V star, and this implies that null space of I minus T equals range of I minus T star perp, and that is 0. Okay, so that completes the proof of this part. Okay, now for the last part, so we want to show that D equals dimension of n of I minus T, and D star is the dimension of n of I minus T star. So to show D equals D star, So assume D is strictly less than D star. So n of I minus t is finite dimensional, implies complemented, implies there exists a projection P from V into onto n of I minus t, continuous projection. Now range of I minus t is n of I minus t star perp. So this implies that range of I minus t has finite codimension d star, okay, and therefore it is complemented. Again, we have seen these things before. So let W be a d star dimensional complement to range of I minus t. Now since D is strictly less than D star assumption, there exists a continuous linear map lambda from n of I minus t into W. These are both finite dimensional spaces, so you can, any linear map is continuous, which is injective but not surjective. You cannot have a surjective map because this has smaller dimension than the other one, and therefore you can have a map which is injective but not surjective. Map a basis to a part of a linear on the basis here. So now define S equals T plus lambda composed with P. Okay, so T is a map from V into itself. P goes from V into the null space and lambda goes from null space into W, and therefore this is all a map of S into V into V. So S belongs to LV. Okay, and T is compact and lambda P is of finite rank. In fact, lambda composed with P has finite rank because its range is inside W, which is finite dimensional and therefore compact. Therefore, sum of compact operators is compact. So S is also compact. Okay. So now, so S is also compact. So let U be such that U minus SU equal to 0. What is that? If you expand that, that is U minus TU plus, or rather minus, lambda time, PU equal to 0. Okay. Now where does this belong? This belongs to range of I minus T, and this belongs to W, which is the complement of the range of the I minus T, and therefore this is a direct sum. Therefore you have written the 0 vector as a sum, one here and one there, so each of them has to be 0. So this implies that U minus TU equal to 0 and lambda PU equal to 0. So this implies that U itself is in null space of I minus T. So this implies that PU equals U, implies lambda U equal to 0, and that implies that U equal to 0 because lambda is injective. And consequently, you have that I minus S is injective, S compact. So by C, range of I minus S is all of V. Okay, so let F belong to W minus the range of lambda. That is what we know, that lambda is not surjective into W, and therefore you can find an F which is not in the range of this. Okay, so now it is S, I minus S is onto, so there exists a U in V such that U minus SU equal to F. So once again let us write that U minus TU minus lambda PU equal to F. Again this belongs to I minus T, range of and this belongs to W. Okay, and therefore again by the direct sum decomposition you have that okay, now F also belongs to W. Okay, this implies that U minus TU belongs to W, and it also belongs to the range of I minus T, and they are complementary spaces. This implies that U minus TU equal to 0, and this implies that F is equal to minus lambda PU, implies F belongs to range of lambda, but that's a contradiction because we have chosen F not to be in the range. Okay, so we have a contradiction all over, and therefore, and that started from the fact that we assume that D is less than D star, and therefore there existed a lambda. Okay, so therefore you have, so this implies that D star is less than or equal to D. Now similarly, dimension of the null space of I minus T star is less than or equal to dimension of the null space of I minus T double star should be less than the dimension of the null space of I minus T star, which is equal to D star. Okay, now if J V to V double star is the canonical embedding, then J of n of I minus T is contained in n of I minus T star, T double star. You can check this. Okay, so this is very trivial checking. All you have to do is to find I minus T double star of Jx, and then apply the definition of T double star, which is, and use the adjoint equation every time, and then you will get that this is equal to 0 because this is equal to 0. Okay, so then therefore now J is isometric isomorphism, so the dimension of this space is precisely D, that is D is less than or equal to D star. And therefore, so this implies that D equals D star, and the theorem is completely proved. Okay, so remark, so we proved that one I minus T compact implies, so then 1 to 1 if and only if on. But this is not generally true for any operator in a Hilbert space, as you have already seen. You take Tx is equal to 0, x1, x2, etc. x equals x1, x2, so on in little l2. Then T is 1, 1, but not on. So in finite dimensional spaces, we also always have that, see, in finite dimensional spaces it's difficult to talk about the null space, dimension of the null space, whereas the dimension of the range is nothing but the column rank is nothing but the number of linearly independent columns, and the dimension of T star, rank of range of T star is nothing but the number of linearly independent rows. So you can say that the row rank is the column rank. But then by the rank nullity theorem, we automatically get that the dimensions of the null spaces also coincide. Now in infinite dimensions, it's difficult to talk about the dimension of the range because they are all infinite dimensional. So there's no point in saying they are equal. Okay, they are both infinity. So whereas the null spaces are finite dimensional, and that is why we state the theorem in this fashion. Okay, the Fredholm alternative. Why do you call it an alternative? Okay, so you have V is a Banach space and T is an LV compact. So one of the alternatives holds. Either the equation u equals tu, u minus tu, sorry, equal to 0 has only the 0 solution, and so the equation u minus tu equal to f has a unique solution for every f in V. Okay, so this is one alternative. Or u minus tu equal to 0 has d independent solutions, then u minus tu equal to f has a solution if and only if it satisfies d compatibility conditions. Namely, that is, we have that f belongs to n of I minus t star perp. So this is a d-dimensional space, so it is being in the orthogonal means it should satisfy it should vanish on each one of the basis elements here, therefore it will vanish over the entire space, and therefore you have that f must be in this it should satisfy d compatibility conditions. Okay, so that is the reason why you have this. Now another remark, in finite dimensions, for instance, you have, if so V is dimension n, okay, so you have V to V, A is some matrix which generates an operator. Let us work with the real space for, or doesn't matter what we are working with. Okay, so we want to look for Ax equal to B solution to solve the n linear equations in n unknowns. Actually, you can do it even for rectangular matrices. When V to W, it doesn't matter, we will do it in this case. So let us assume that y belongs to so A star y equal to 0. Then y transpose Ax, which is y transpose B, which is yb in a product, is equal to yax equals A star y x, and that is 0. Okay, so this means that if you have a solution to this equation, then a necessary condition is that B belongs to kernel of A star perp. Okay, or in our language, n of A star perp. Okay, so range of A is contained in null space of A star perp. Okay, so this means that the dimension of the range of A is less than or equal to dimension of null star of A, null space of A star perp, which is equal to n minus dimension of the range of A star perp. N minus dimension of null space of A star, because the perp is a complement, and that is equal to dimension of the range of A star. So dimension of range of A is less than equal to dimension of range of A star, and if you apply it to A star now, so dimension of range of A star is less than equal to dimension of range of A double star, but that's same as range of A. A double star is the same as A, and therefore you have this, and consequently this is precisely so you have dimension of the range of A equals dimension of the range of A star, and this is saying the row rank is the same as column rank in the real case. In the complex case it says column rank of the conjugate transpose, but conjugate transpose and transpose have the same rank, column rank, and therefore it's the dimension of row rank equals column rank. That is this theorem, and this is also by the rank nullity theorem. This shows the dimension of null space of A equals dimension of null space of A star. And we have also proved, because you have range of A is contained in null space of A star perp, and both have the same dimension, and therefore this also implies that range of A equals null space of A star perp. So all the theorems we prove in just 2 lines using these arguments. Okay, final remark. This Fredholm theory, Riesz-Fredholm theory is the starting point of the study of Fredholm operator. So Fredholm operator A from V to W Banach spaces, okay, is such that NA, dimension NA is finite, codimension of range of A is also finite. Then it's called a Fredholm operator, and you call IA, which is the Fredholm index, equals dimension of NA minus codimension of the range of A. So that if A equals I minus T, compact perturbation of identity, the V equals W, then it's a Fredholm operator with I equals I of A equal to 0. So that is the theorem which we have proved. Okay, so this is a very important concept in operator theory, and okay, so